Example 7.5. Calculate the wavelength of the particle in the following two cases. Case A. The first test serve in tennis is about 150 miles per hour or 68 meters per second. So 150 miles per hour is 68 meters per second, which is the speed of this traveling tennis, or the velocity of this traveling tennis. Calculate the wavelength associated with 6.0 times 10 to the power minus 2 kilogram of a tennis ball traveling at this speed. So let's tackle question A, and we have in mind the Broglie relationship of a wave and a particle. And the formula for the Broglie is wavelength equals to Planck's constant h divided by mass in kilogram times the velocity of the particle. Now I do know that Planck's constant is 6.626 times 10 to the power negative 34 joules second. I also know that my mass is given as 6.0 times 10 to the power minus 2 kilogram. And I know that my velocity is given as 68 meters per second. And I also know that 1 joule is equivalent to 1 kilogram meter squared per second squared. So these are the things I know in preparation to doing my calculations. So let's find the wavelength associated with 6 times 10 to the power minus 2 kilogram mass of a tennis ball. So the wavelength lambda is going to be equal to 6.626 times 10 to the power negative 34. And remember, this is joules seconds. That's the h value, Planck's constant. And then I'm dividing that by the product of mass and velocity. The mass of this tennis is 6 exponent negative 2, meaning 6 times 10 to the power negative 2 kilograms. I'm saving space by using an E. And then the velocity is given as 68 meters per second. Now, I need to write that joules in this form. So my wavelength is going to be equal to 6.626 times 10 to the power minus 34. Where the joules is, I'll put kilogram meter squared over second squared, and then times this second here. In chemistry, all units must cancel out, which is why I had to convert the joules to kilogram meter squared over second squared. Because then, how am I going to get rid of the J if I don't do that? Or even the kilogram. So I'll copy my numbers again. That's the mass, and this 68 meters per second is the velocity. Okay, so now what I have here and what I can already see is that my kilogram and my kilogram will cancel out. This meter will cancel out with one of the meter squared, so I'm left with an M. And then this S will cancel out with one of the S squared, you're left with an S. Okay? And then this denominator S will cancel out with this denominator S. Now you can see why I wanted to convert the joules to kilogram meter squared per second squared. The only unit left is a meter, which is good because we are looking for wavelength. So let's do the math. So my wavelength will be equal to, so you want to take this value and divide by the product of these two, the multiplication of those two. Let's do that. So I have 6.626 exponent 34, it has to be a negative, and then I'm going to divide that by the multiplication of 6 exponent negative 2, which is multiplied by 68. Close my parentheses, and my answer is 1.624 exponent minus 34. 1.624 times 10 to the exponent minus 34. Remember, our unit that survived was a meter. Okay, if you want to convert this to nanometers, you will simply multiply this by 10 to the power 9. So let me multiply my answer by 1 exponent 9. So it becomes wavelength equals to 1.624 times 10 to the power negative 25 nanometers. That is quite a small wavelength, very tiny wavelength. That tells you that the tennis ball cannot have a wavelength property, because the wavelength is always the distance between crest to crest. Now, if that distance does not exist, the tennis ball cannot have a wave property, which means it's an object. Just like you and I, we don't have wavelength. A car does not have wavelength. Our mass is big, and when we travel, our velocity is also going to be bigger, and so we don't have a wavelength. We are objects. The tennis ball is an object. You see now the use of de Broglie's equation. It helps you to decide if the particle or the matter in question can have a wave property or not, if it's microscopic or macroscopic. In this case, the tennis ball is macro, is big. It's not microscopic. There's no wavelength. It's macroscopic. Macro with an A. It's an object. So that is the answer we are looking for, and this would be the wavelength, if at all it would have existed. But now we see it's so small, tennis ball does not have a wavelength. It's not microscopic, it's macroscopic. Oh, by the way, we always want to report our answer to the correct sig figs, in this case 2 significant figures, as 68 or as 6.0. So it will be 1.6, because the 2 is less than 5, times 10 to the power minus 25 nanometers, or in meters, you would have reported it as 1.6 times 10 to the power minus 34 meters. So the final answer is either 1.6 times 10 to the power minus 25 nanometers, or 1.6 times 10 to the power minus 34 meters. Either way, those wavelengths are too small to exist. The tennis ball is an object. It's macroscopic, not microscopic, which is how this answer was found here. That said, the calculation and cancellation of units are not shown. So I've shown you how you can convert a joule to kilogram meter squared per second squared, and use that to cancel out the SI units to be left with just a meter. So we've answered part A and determined that the wavelength associated with 6 times 10 to the power minus 2 kilogram tennis ball traveling at 68 meters per second is 1.6 times 10 to the power minus 25 nanometers. It's too small. That does not exist. The path traveled by the tennis ball cannot have a wavelength. The tennis ball is too big. It's macroscopic. It's an object. Now let's answer part B. Part B of this question concerning the Broglie equation reads: calculate the wavelength associated with an electron that has a mass of 9.1094 times 10 to the power minus 31 kilograms. We know that's the mass of an electron as found by Millikan's experiment, moving at 68 meters per second. So now let's see if this electron is small enough to have a wavelength if it is microscopic according to de Broglie's equation. So again, to reread the question, calculate the wavelength associated with an electron having this mass moving at 68 meters per second. So what you're going to do is to write our equation, and the equation is wavelength lambda is equals to Planck's constant h over mass in kilogram of the particle or the matter times velocity, okay, which is loosely called speed. Velocity is speed in a given direction. So we know again that Planck's constant is 6.626 times 10 to the power minus 34 joules seconds. It's always good to write what you have or what you're given before you even begin. I also know that the velocity is 68 meters per second. Notice that it's meters per second. I also know that 1 joule is equivalent to 1 kilogram meter squared per second squared. This is not given in the problem, but is something, or it's a relationship that you must keep in mind so that all units will cancel out. So now all that is left for me to do is to plug in the values in my formula. So wavelength will be equal to 6.626 times 10 to the power minus 34 joules seconds. I'm dividing that by the product of the mass and velocity. The mass has to be in kilograms, so 1.094 times 10 to the power minus 31 kilogram is the mass of one electron, and the velocity of these electrons given as 68 meters per second. Now, as you can tell, we need to find the wavelength, meaning our final answer should be in meters, but we have a kg, we have joules, they will never cancel out. Okay, so this J here has to be converted to that unit, or that SI unit, group of SI units. So the wavelength will be equal to 6.626 times 10 to the power minus 34. Where J is, I'm going to put kilogram meter squared per second squared, and then don't forget the S that was there before. Now I have units that can cancel out up and down. The mass again is 9.1094 times 10 to the power minus 31 kilogram. I'm multiplying that by 68 meters per second. Now I do know that this second will cancel out with one of the second squared. Second squared is like S times S, so I'll be left with an S here. This meter is gonna cancel out with one of the meter squared. Meter squared is like M times M, so I'll be left with 1 M there. And then this second down here, the denominator, is gonna cancel out with the remaining second, the denominator in the numerator. So the surviving unit is only the meter. Only the meter survives, which is good because our wavelength will be in meters and can convert it to nanometers if need be. So now what is left is for me to punch in the numbers and to find my wavelength. So let's bring up our calculator. So I'll put my Planck's constant 6.626 exponent minus 34. I'll divide that by the product of the mass of the electron. Let me move this there. The mass of the electron is 9.1094 exponent minus 31. I'm multiplying that by 68. Parenthesis closed, equal sign. So I have 1.0696. So this is like 1.070 times 10 to the power minus 5. I see E minus 5 there. So it's 1.070 times 10 to the power minus 5. Remember, our surviving unit of measurement was just a meter after cancellation of units. Okay. Now, you might say that this is small. Usually wavelengths are quite tiny, so we have to convert this to nanometers. So it will be 1.070 times 10 to the power minus 5 meters, and then we're going to use a conversion factor, which is 1 times 10 to the power 9 nanometers is equivalent to 1 meter. That way, the m and the m will cancel out. Our answer will read something nanometers. Okay, because this unit nm survives. Okay, so the answer here would be 1.070 times 10 to the power, so minus 5 plus 9 should be 4. I don't need a calculator for that. And this is approximately equal to two significant figures. Here is approximately 1.1 because the 7 is greater than 5, so I'll round up the 0 to 1 times 10 to the power 4 nanometers. And by the way, this answer we found here is in the IR region. So what does that tell you? That tells you that the electron is small enough to move in a path that's gonna have a wavelength. The electron is microscopic. It's not an object like you and I. And it's true because the mass is quite small. You see, in the Broglie equation, wavelength equals to mass times velocity. So if the mass here is very small, okay, if the mass is very small, that would tell you the corresponding wavelength is going to be very high. And if the wavelength is high, then you have a microscopic property of that particle or matter, which is an electron. A tennis ball had a larger mass, therefore the wavelength was so low, almost not non-existent, or you would say non-existent. So a tennis ball, or you and I, or a car, or a truck, or a house, those are macroscopic. Okay, they're big, but then an electron is microscopic. It does have a wavelength. It's quite tiny. And based on the Broglie equation that we used here, since an electron has mass property, which is 9.1094 times 10 to the power minus 31 kg, although small, and it has wave-like property, which is 1.1 for this case, 1.1 times 10 to the power 4 nanometers. Since he has both mass property and wave property, then de Broglie is correct to say that an electron has dual properties. An electron has double property. An electron can behave as a wave, an electron can behave as a particle. So he proved the dual nature of an electron, behaving as a wave because of the wavelength property, behaving as a particle because of the mass property. The tennis ball lacked the wavelength property. The tennis ball had bigger mass, so tennis ball is only a particle, but does not have the wave property, because the wavelength that we calculated was quite small. The wavelength that we calculated for the tennis ball here is quite small, 10 to the power minus 34. So the tennis ball is just a particle but does not have a wave property. This 1.1 times 10 to the power 4 nanometers is in the IR region, and if you doubt, let me show you in your notes. This is like 11,000, I believe. Yeah, 1.1 times 10 to the power 4 is the same as 11,000 nanometers. Here's our electromagnetic spectrum. The 1.1 times 10 to the power 4 nanometers lies somewhere between here, which of course is the IR region. So an electron is microscopic, quite tiny, such that it can have a wavelength. And that concludes the answer to that problem. Here is another question exploring the Broglie's, the scientist's wave-particle duality nature equation. And that equation, I'll keep reminding you, is that wavelength, the wave property of a particle, will be equal to Planck's constant h times the mass of the particle or matter in kilograms times the velocity in meters per second. So let's read the question. Practice exercise. Calculate the wavelength in nanometers of a hydrogen atom whose mass is 1.674 times 10 to the power minus 27 kilograms, moving at 7 times 10 to the power 2 centimeters per second. We are trying to get to this answer. So here comes the process. First of all, list down what you're given, because if you don't know what you're given, how will you get what you're looking for? So you're given here the mass of our hydrogen to be 1.674 times 10 to the power minus 27 kilograms. That could be equal to a mass of a proton anyway. And then you're also given the velocity. Velocity V is given as 7.00 times 10 to the power 2 centimeters per second. Notice the units. What also we should know is Planck's constant. Planck's constant must also be identified as 6.626 times 10 to the power minus 34 joules seconds. Okay. And the other thing that I want you to know is a unit that will help you to cancel out the joules or to get rid of the joules. 1 joule again equals to 1 kilogram meter squared per second squared. So these are the things that we need to solve this problem. So here we go. Our wavelength is equal to Planck's constant divided by meters times velocity. Our Planck's constant is 6.626 times 10 to the power minus 34 joules seconds. That joule needs to be gotten rid of because it will not cancel with any other thing. And then divide by the mass of the proton is 1.674 times 10 to the power minus 27 kilograms, multiplied by the velocity, which is 7.00 times 10 to the power 2 centimeters per second. Now, one thing I want to, or two things I need to do, I need to convert this joules somewhat to read kilograms meter second somewhat, so that there will be cancellations of units. Also, I want my centimeter to read somewhat meters. So I'm going to do a side conversion of this centimeter per second to meters per second, which will be 7.00 times 10 to the power 2 centimeter per second. I know that 1 meter is equivalent to 100 centimeters. Hey, you need to know your conversion factors. cm and cm will go. So the answer here will be 7.00 times 10 to the power times 10 to the power 0, actually, meters per second. This just means it's 7.00 meters per second. Okay. So now I have my velocity with the right units. This joules is going to be replaced by these units you see here to the right. I'm highlighting that. It's going to be replaced by those units so that there will be cancellation of units. So now I can come here and rewrite this as 6.626 times 10 to the power negative 34. Where the joules is, I'm going to put kg meter squared over second squared, and then I'm not forgetting this s here. It's gonna be this s. And now I should be able to cancel a bunch of SI units here. So I bring back my number 1.674 times 10 to the power negative 27 kilogram. That's the mass of the proton. And multiply, this time I'm going to use my velocity in meters per second, 7.00 meters per second. Now, having these units like this will help me to cancel kg and kg. In chemistry, SI units must cancel out. You have to be very careful. Okay, this s is gonna cancel with one of the s's in s squared to be left with only one s. And then that one s is gonna cancel out with this s in the denominator, and one of the meter squared will cancel with this meter to be left with only an m, which is what we want because we are looking for wave length. The basic SI unit for length should be a meter. Now things have cancelled out beautifully. I know that I'm gonna be left with the meter, so now all I need to do is to punch in the numbers in my calculator. Here's my calculator, so I'm going to do 6.626 exponent 34 but a negative of it, and then I'm dividing it by the product of the denominator, which is 1.674 exponent minus 27 multiplied by 7, close by parentheses. So my answer is gonna be 5.655. I can round the 4 here to a 5. 5.655 times 10 to the power negative 8 exponent negative 8. So the answer here is in meters m. The question, if you go back to the question, it wants you and I to calculate the wavelength in nanometers of a hydrogen atom with a mass of 1.674 times 10 to the power minus 27 kilograms moving at a velocity of 7 times 10 to the power 2 centimeters per second. So now I need to do some conversions here. So to convert this answer to nanometers, I know that 1 times 10 to the power 9 nanometers is equivalent to 1 meter. Doing so, again, my units are cancelling out. So my wavelength in nanometers would be 5.655 times 10 to the power minus 8. Since it's 10 to the minus 8, 10 to the power 9 is like adding a 9 up here. And that is 5.655 times 10 to the power 1, which is just 56.55. Remember the surviving units is nanometers, so nanometers. So my wavelength is 56.55 nanometers. Now I can report it to 3 significant figures. I see I have 7.00. Those zeros are significant. So my wavelength will be equal to, I need to stop here. I see that 5 equals to 5, so I'll round the 5 to 6 here. That 5 will be rounded to 6, so it will be 56.6 nanometers. The answer given here is 56.6 nanometers. So we're good. That's the final answer asked for. Done.